Here's a question. I hand you a whole number, like 121. Does it read the same forwards as it does backwards? 121 does. Flip it around, you still get 121. But 10 flipped reads 01. Different. Let's pin down the rules. Take 121, left to right, then right to left, the digits match. So we answer true. 2 traps. -121 flipped lands the minus sign last, so negatives are always false. And 10 flipped reads 01. False. What would you try first? Probably the obvious move. Reverse the whole number, then check if it matches the original. Take 121, peel the digits off the back one at a time, and build a brand new number. You get 121 back. Compare the reversed number to the original. They're equal, so it's a palindrome. That works. So what's the problem? Here's the catch. The input can be enormous, all the way up to the largest 32-bit integer a computer can hold. Reverse a number that big, and the flipped version can shoot past that limit. In a fixed-size integer, it overflows into garbage. Look at what we just did. We rebuilt the entire number, then compared. But think about what a palindrome really is. Its front half mirrors its back half, and the middle digit, if there even is one, never matters at all. So here's the question, why reverse the whole thing? What if we only reverse the back half? That's the move. Half reversal. Peel digits off the back into a new number, and shave those same digits off the front. You might think you need to count the digits first to find the middle. You don't. There's an easier signal. Watch the two numbers. The moment the reversed back half is greater than or equal to the shrinking front, stop. They've met in the middle. Let's trace 121. Two numbers on the board. X holds 121, and the reversed half starts at 0. First, the guard. 121 is positive, and it doesn't end in 0. Both checks pass, so we move on. Round 1. Is X greater than the reversed half? 121 beats 0 easily, so we step into the loop. Take the last digit of X, which is 1. Push it onto the reversed half. It goes from 0 to 1. Now chop that digit off X. 121 divided by 10, ignoring the remainder, leaves 12. X is now 12. Round 2. 12 still beats 1. The last digit is 2. Push it on, and the reversed half goes from 1 to 12. Chop X once more. 12 divided by 10 is 1. Now X holds 1, and the reversed half holds 12. Check the loop again. Is 1 greater than 12? No. The loop stops. We've reached the middle. Now compare. X is 1, the reversed half is 12. Not equal. Did we just fail? Not yet. 121 has an odd digit count, so the reversed half still holds the middle digit. Drop it. Now 1 equals 1. True. Notice what we never did. We never built the full number. We only ever held half of it, so it could never overflow. How fast is this? Each pass drops 1 digit, and we stop halfway. So the work grows with the number of digits. And memory. We use one extra number, the reversed half, and nothing more. The space never grows. It stays constant. Same logic now in Python. The signature matches the starter code. One integer goes in, true or false comes out. First the guard. Negatives fail, and any number ending in 0 fails too, unless the number is 0 itself. Set the reversed half to 0, then loop while X is still greater than it. That loop is what walks us to the middle. Inside, push X's last digit onto the reversed half, then chop that digit of X with integer division. At the end, compare. Even length, the halves match directly. Odd length, drop the middle digit from the reversed half first. And that's the trick. Don't do the whole job when half of it answers the question. Reverse to the middle and stop.